Welcome everyone. Welcome to this 𝗙𝗍𝘀 𝗍𝗲. We are constantly pushing the boundaries of the control of high-tech systems to what is physically possible. At these boundaries, we can no longer assume the availability of highly accurate models. Instead, we have to take uncertainty in the system and in its environment into account explicitly. AI is here to guide us in this uncertain world. Today, we will be exploring new AI techniques based on Bayesian learning and see how these techniques can be used in the world of high-tech systems. My name is 𝗙𝗿𝘀_𝗺𝗀. I'm head of the Mathware department at Sioux Technologies, a team of 50 mathematicians, physicists, and data scientists. And one of our core competences is deep learning, where we follow recent advances in the field. As such, I'm really proud to announce today's keynote speaker, Professor 𝗱𝗿𝗺_𝗀 of Bayes Lab, who will take us, reveal a glimpse of the future to us. Using neuro-inspired techniques, Bert is going to explain how we can add self-learning mechanisms to our conventional system models. And such AI models no longer claim to a priori know the world around it, but based on new observations are capable to improve their understanding of the world and thereby their performance. After the keynote presentation of Professor de Vries, Bas van der Linden will present. Bas is Technology Director at Sioux, and he will put this new Bayesian hype into perspective and show how, in practice, we can incorporate these new techniques in high-tech system design. Before starting with our main speakers, however, we will be looking at the recent King's Days performance as an inspiring example. We highly appreciate your contribution to this event here in the audience and at home. So please feel free to have a lively discussion and ask questions. But for a smooth program, we will collect the discussion at the end of the presentation. You can already post your questions in the chat. I wish you all a very inspiring event. And I would like to start by going to the King's Day event, which was about the unpredictability of human beings, surrounded by 12 drones with razor-sharp blades, a singer, a dancer, an audience of millions of viewers on the television, and the king, of course. That must have been quite exciting. How was that, Stijn and Ruben? Maybe you can introduce yourself briefly.
Yeah, I'm Stijn Groen. I'm an electronics engineer at Sioux, and after my graduation internship 2 years ago, I've been working here.
Yeah, and I'm Ruben Kwant. I work for the Mathware department, now around 4 years at Sioux. And indeed, I also worked on this project where we got to perform or help perform a show with drones for the king.
Great. Let's maybe first whet our appetites by having a look at a fragment of the show.
Eigenlijk onderzoekt ons stuk de rol van de technologie in ons leven als sociale wezens eigenlijk.
Sunrise hues in mighty kettle steam, play through glass that keeps out the breeze. Someday we'll learn why we still speak. Lately I know whether.
An exciting show, a lot of dynamics going on, but what we didn't see here yet is the king, the queen, the royal family watching from up close. That must have been exciting for you guys.
Yeah, it was really cool. It's really weird. Like we do a lot of projects, but it's really a really weird feeling to know that the king and his family will be watching the project you're doing, and you're showing it to the entirety of the Netherlands. That was really cool.
Yeah, I can imagine. This hasn't been the first time, though, that you have been working with drones. Can you explain a bit more?
Yeah, so the collaboration started now around 3 years ago, where the dance group, Another Kind of Blue, and Sioux came in contact, where they wanted to do a show with drones, and they had multiple parties involved, and we were asked to develop the control software for the drones. And so we went into this project, but really we ran into a lot of issues, mainly also with parts of the drones which we weren't making, the communication between the central computer and the drones, because it was really outdated. So then for this project, we decided to also incorporate that to really make it run extremely smoothly.
Yeah. So yeah, you're talking about communication protocols, the control of drones. I mean, these are elements that we know from the high-tech industries and the machines that we encounter there. But yeah, it might seem quite atypical to encounter such a cultural show, basically, as Sioux.
Yeah, so I don't think it's that strange. I think so. I really think you can show what you can do with technology in every aspect of the world around us, and I also think as a company we want to do that. And here we use a really fun project to also learn more things about the new technologies happening around us: drones, communication protocols, control loops, whatever. And I really think that's really cool.
Right, that sounds quite multidisciplinary, to be honest. So you could also see this project as a training ground for combining all these techniques, then I suppose.
Yeah, for sure. The project in the beginning, we got to hear, okay, we've got 10 weeks to complete this all, and then you really need to really work together on this to get everything done in those 10 weeks.
Right. Yeah. What were the main challenges that you encountered in these 10 weeks, and what technological lessons basically let you learn in this pressure cooker?
Yeah, so the main thing was the time allocation that we had, 10 weeks to develop a complete new communication system and upgrade the drones to have better working performance eventually. And so we needed also to take into account the design, the research, but also production and maybe errors that could occur. So we had to do a lot of parallel processing to, even during the research phase, also start designing the board and also start on the software that runs on these boards. Yeah. So there was a lot of things involved at the same time.
Yeah, and I also think all these things which were involved had to come together and then also still keep working. And I really think that was one of the risks at the start, which luckily it all went well, but it was really until everything came together, there were a lot of nerves if this would work. Yeah.
And getting things come together aspect is, of course, you can look at that from a technological point of view, the challenge is there. But there's also the interaction with the show, basically. Another Kind of Blue has been our cultural partner in developing this show. Can you tell something about that interaction with them?
So indeed you have to work. So basically, as an engineer, you now have to work together with a dance group, which is always a bit weird because, well, typically we're used to very set requirements and specifications. Yeah. And now the specification was, well, at least it has to look nice, which was a new one for me. Yeah. So it was really working together with him. It was really fun, but sometimes a challenge.
Yeah. And as I mentioned before, I know that there have been earlier shows with another kind of blue, but yeah, this time also the singer 𝗙𝗍𝘀 was involved. So basically the interactive part even got increased in dynamics, I suppose.
Yeah, because 𝗙𝗍𝘀 also uses her gloves to change the music a bit, and then so we basically we can set up the technology, and then they are the ones who have to execute it. So during the show, parts of the music was controlled by her gloves. Her hands also controlled the drones at some point.
Yeah.
And then we had to make sure that whatever she was doing, basically, it remains safe enough, or at least consistent enough that she could do that.
Right. Let's have a look at another fragment that we have collected to show the actors basically of the piece.
Normaal sta ik op straat met Koningsdag en dan ben ik aan het feesten. Dus ik weet niet of ik wel ja wil zeggen hierop. Maar toen hoorde ik wat het plan was. En vooral dat ik samen met David en die drones zou gaan werken. En dat is wel echt een once in a lifetime. Want ik was gewoon al een groot fan. Dus ik vond het echt heel erg bijzonder en heel leuk dat ze dat met mij wilden doen.
Voor een deel ben ik denk ik ook de aanstichter. Ik ben heel lang geleden begonnen met het maken van voorstellingen met een drone. En daarbij had ik eigenlijk al de droom om iets te maken wat zo interactief is als deze voorstelling.
In this video fragment, I think you really nicely see the interaction between dancers and technology. It's very nice. As you have already mentioned, the initiative for the show, it started some 10 weeks before the actual performance. So indeed, there was a lot of time pressure. Maybe Stijn, you can talk a little bit more about the technical challenge and how you handled the time pressure aspect there.
Yeah. So as I said earlier, we started to do a lot of things in parallel, which made the project go. Made it also a bit more difficult, but also when it eventually worked, it was also very rewarding to see eventually the drones fly and the communication work. There were a couple of hiccups in the trying out, but eventually when we got at the place where we could put the show up, we didn't have any problems anymore with the communication system, so that was really nice.
And what was the main challenge in the communication system?
Yeah, so the main challenge in the system before, they used the normal Wi-Fi frequencies, which was not optimal because there were also a couple of, for example, 𝗙𝗍𝘀 also used Wi-Fi in a show, and people in the audience may have phones which interfere with those signals. So getting a different spectrum where you can also get the bandwidth and all the data that you need onto the drones was a tough aspect.
Okay, so this frequency band selection, basically, that has been an important part that you've engineered.
Yeah.
I also learned that you have developed some other new features on the drones for show elements, basically.
Yeah, so before in the Airman show, the drones had a very small board of LEDs, which only faced one way. And that's also something that David said he wanted to do, have more light or try to eliminate subjects that were flying or that it was flying above. So we also upgraded the boards with the LEDs. So we added 2 boards at the bottom of the drone, which, then you can, with those boards you can also change the color and also the intensity of the LEDs, which was really, really beautiful in the show itself, because you could also see the drones interacting with the dancers more.
Yeah. And about the interaction of the drones and the dancers, so you've now talked about the communication basically and the lighting of the drones, but how does the interaction with the dancer look like? Can you explain a little bit?
Yeah, so you can see it on the image which is now also here on the screen. You see that 𝗙𝗍𝘀 in this instance has all those tiny bulbs on her suit. These are basically tracked by a motion capture system which is around here. And we then get the movements that she makes and transform these into movements that the drone should make. Okay. And well, this is, and then of course the difficult part as well, how do we also sort of keep track of where the drone is and make sure that they don't crash into each other, which in the end was done mainly also by telling 𝗙𝗍𝘀 or instructing her to not do every movement possible because, well, some movements are just impossible for the drones to make, and then you can run into problems.
Okay, I think that's a nice cue of what we're talking about tonight, because it basically means that the dancer, the drones, the tracking system, it's all part of a big system that is subject to uncertainties and environmental disturbances, I guess.
Yeah, exactly. And I'm also really curious about the next presentation, because I indeed think, I was thinking by myself, if it's in some way we can already predict the movement of the dancers, then you could look ahead in the future and use that to basically already try to predict a path which is better suited for the drones, even no matter which movement the dancers make.
Yeah. Let's maybe have a look at another fragment that illustrates the tracking of the drones, the tracking of the dancer by the drones.
Maar toen bleek dat mijn handschoenen niet meer konden connecten. En mijn vermoeden is dat ook alle data van het mocap systeem deze kant op worden gestuurd en dus de verbinding blokkeren.
We moeten allerlei dingen met elkaar laten communiceren. We hebben bijvoorbeeld hier het systeem op positie bepaald. Bij de 𝗙𝗍𝗁𝘀 handschoenen die moeten ook daarop aangesloten worden. Want daarmee past ze dan de muziek aan die weer hier vandaan gestreamd wordt. En op dit moment, op het moment dat wij dingen naar haar beginnen te sturen, stoppen haar handschoenen met werken. En we weten dat niet waar.
Ja, het werkt.
In dit stuk stuurt op een gegeven moment de zangeres 𝗙𝗍𝗁 de drones live aan. Waar ze dan bijvoorbeeld haar armen gebruikt om de drones aan te sturen. Daar zitten dan ook van die bolletjes op die de positie detecteert.
Yeah, so I have myself watched this show on King's Day, and I must say in the audience, if you have not been instructed, I mean the real challenge is the live tracking part during the show, of course.
Yeah.
So yeah, it's not pre-programmed, right?
No, there really are parts of the show which are live. So sometimes it seems as if if they are just following around a pre-programmed path, and also for parts of the show that's true. But indeed, when she starts moving her arms around, we hit the switch and they start following it live, and really whatever she does, the drones will try to follow.
Yeah, I think that's also culturally the philosophy of David Middendorp, a beautiful illustration of man-machine cooperation.
Exactly.
Yeah. Yeah, it looks easy looking at the previous video, but apparently it has not been, and we have an example from that as well.
Yeah, indeed. But so what I really like is no matter how large the challenges are, you could hear me screaming in enthusiasm when it started working. It's really the harder the challenge, the more elevated you become when you solve it.
Yeah, exactly. Let's have a look at the video when things didn't go completely as planned. Unfortunately for you guys, we also have some video from that.
Dat alles goed gaat en dat die drones niet tegen de mensen die er echt heel erg dicht in de buurt staan aanbotsen.
Een van de moeilijkste dingen om op te lossen is dat je vaak niet weet wat er fout gaat. Dus zoals net ook, dat de drones naar beneden vallen. We weten niet waar het probleem zit en dan moeten we dus gaan uitvogelen waarom er nou een probleem opkomt.
Maar er is niks in de propeller gekomen, toch?
Wacht ik niet, nee.
Dat heeft gewoon... Ja, oké. Maar dan vind ik het een verklaarbare fout. Want inderdaad, op het moment dat zijn propeller opgeblazen wordt en hij probeert dingen te doen, dan begint hij gewoon te spinnen.
Ja, maar de vraag is, waarom blaast die propeller op?
Ja, was die al eerder kapot?
Ja, dat weet ik niet.
Er zat al een scheurtje in.
Maar
Kijk, dit is het punt waarschijnlijk waar de landing ingezet werd. Ja. Waar de landing gestart werd. Maar dus, hij gaat gewoon omlaag, nou prima. Maar hij gaat ook opzij.
Er gebeurt iets en dan moeten we meteen gaan kijken van oké, ligt het aan de computer, ligt het aan de software, ligt het aan de drone zelf, ligt het aan de communicatie. Dus we moeten alles gaan nalopen om te controleren of alles goed werkt.
Does this happen a lot, guys?
Yes.
In the beginning it did, yeah.
Yeah, it's really indeed. So something goes wrong after you've integrated everything, and then you start discussing what went wrong. Is it a hardware problem? Is it a communication issue? It's somewhere on the interface. Typically, that's what went wrong. I often said that it was Stijn's fault, and then he started accusing me back that it was my fault.
Yeah. But that's the very nice thing about this multidisciplinary project, is that we were there with all the disciplines at the same time. So if something went wrong, we could start debugging, and everyone has their own expertise and can look at their own data to see if something in their part went wrong.
Yeah, that's also shows from the video. It's great to see you working together in the lab to get the thing up and running.
I think in the end it was a propeller which was already broken.
Yes. I think this is a very, very nice show, and I can imagine that it's even more impressive. I mean, we saw it on television now, but if you see it in real life and see the interaction with the dancers in the theater, I think this even adds something to the show. Is it possible to see live performances of the show?
Yeah, so Another Kind of Blue will be touring again with their previous show, so Airmen, where they're also flying with drones, and they are planning to also sell the 𝗱𝗿𝚀, but they're still figuring out on how to do that.
And yeah, the
King's Day show.
Right. And you already said that, yeah, you have a lot of ideas how the topic of today can be used as an inspiration for future shows where maybe the range of movements can be further expanded still, and the interaction with the dancers can be extended.
Yeah, and I also think David Middendorp, the choreographer of the show, he had some idea where he indeed really wanted the drones to autonomously form a dancer and let them decide the path on their own, which would really be, I think, the final extension of what we can do here.
Okay. You will keep us posted.
I will keep you posted.
Very good. Well, thank you very much for the nice interview.
Thank you.
Let's have a final look at some footage from the video, and thank you very much for today.
Het is wel belangrijk dat het werkt, maar de magie begint pas als het werkt en je kan daarna je gevoel er weer in stoppen en dat die extra laag erbovenop doen. En zeker ook als ik maar niet meer nadenk over die technologie en me helemaal kan gaan verliezen in dat lied. Dat is wanneer we de mensen gaan raken.
Chasing, we're only involved. Whatever's between us isn't your fault. Wherever it ends up is where it belongs.
So then it's time to announce the keynote speaker of this afternoon, Professor 𝗱𝗿𝗀𝘀. He is affiliated with the signal processing group at the Eindhoven University of Technology and Bias Lab. His research focuses on intelligent autonomous systems and their interaction with the environment. And draws inspiration from various fields: computational neuroscience, Bayesian machine learning, signal processing. Yeah, very curious to hear your presentation, and glad to have you here tonight. The floor is yours.
Thank you, Robert. Thank you for your kind introduction. Thank you, Bas, for the invitation. This drone stuff really looks like a fantastic project, and I hope I can talk a little bit about the research that we're doing at our lab, and perhaps in the discussion we can make some connections. Just to position what I'm going to be talking about, this is a hype curve, or sort of an expectation life cycle for emerging technologies. It's about 2 years old, and 2 years ago, deep learning was really on top. People had the idea, yeah, deep learning is going to solve everything, right? And so the last few years, we are finding out, well, deep learning is going to be a fantastic technology, but there are also some limitations in the really big data set. It's not very adaptive once you have learned it, and you often need to label all this big data set. So it's very sort of labor intensive. And so the question is there something that comes after that? Well, we don't know yet what that's going to be. On my graph, I'm not sure if you can read that, but in the blue circle on the left bottom, I encircled the area that we are working on. There are terms like human augmentation and artificial general intelligence. I like to call it nature-inspired or natural AI. And so that's what I want to be talking about today. So we do this research at Bayesian Lab. Bayesian Lab is a subgroup at the Department of Electrical Engineering in Eindhoven here. Like I said, our work is inspired by how the brain works, by a particular theory called the free energy principle. I'm going to be talking about that. We do this research with two postdocs. On the left-hand side, bottom left, is 𝗱𝗿ecie, who is also here and is a part-time employee of Sioux. Then 𝗙𝗿liche𝗺𝗪 is another postdoc, and 6 PhD students. I'd like to mention them. Ismail Senyos, Sami Akbayrak, Magnus Kudal, Albert Podusenko, Dimitri Bagaev, and Bart van Erp. Very international group, and I want to mention them because most of what I'll be talking about is due to their credit. So let me start just by an introductory example of what we're interested in. I also work for a hearing aid company. So we are in the business of designing hearing aids. And hearing aids, inside the hearing aid is an algorithm, an audio algorithm. It has like 60, 70 parameters. And yeah, we have to tune these parameters to, well, to maximize the satisfaction of the patient. And usually, well, the patient goes to 𝗱𝗿𝗀𝘀𝘁𝗲𝘀 or 𝗱𝗇𝗺berg and leaves quite happily. But we can't predict how the world works, so something will always happen. A week, 2 weeks, 3 weeks later, she'll be at a restaurant and can't understand her conversation partner. Well, what's she to do? You can't ask a patient to tune 60 parameters. So she goes back to the audiologist. Yeah, the situation is gone. It's very hard to reproduce the situation. You can't ask an audiologist to tune 60 parameters. So in the end, if there's enough complaints, it goes back to our desks at GN, the hearing aid firm that I work for, and then we start as engineers working on MATLAB and making new algorithms. And then half a year later, they say, well, time is up. We take it away. We're going to recode it in assembler, and then it has to be tested, and then marketing gets involved. So it takes a year before there's a new product on the market. So, and that's a big problem, because by that time, if the problem hasn't been solved, there's a chance that this lady gets disappointed with her hearing aid. And indeed, about 20% of hearing aids still end up unused in the drawer. And it's mainly due because we have so many people in the design loop. And therefore it takes months and often years just to go around our design cycle. Now I want to contrast that to how nature designs algorithms, and particularly our brain. Our brain is also an algorithm designer. Our brain designs algorithms for speech recognition and hearing and object recognition, locomotion, navigation. You can learn Japanese if you want. And it seems to work just in real time. It's a spontaneous process. There are no engineers in the loop. It happens in real time just through spontaneous interactions with your environment, right? You can learn how to ride a bike. You don't have to read, to make the analogy to deep learning, you don't have to read a meter of books. You just go out, you ride, you change your steering wheel, and over time you learn how to ride a bike. There doesn't seem to be a big database involved. So I'm interested in that. I want to know what's going on there. How is the brain capable of learning these algorithms automatically? And can we use that in engineering? So it turns out that if you then go to the physics of spontaneous processes, we wanted to learn, okay, how do spontaneous processes take place in the real world? And then you find out that, well, this is associated with something called free energy, Gibbs free energy or Helmholtz free energy, but it's a measure that you can associate with a system, and as time moves on, if after some time the free energy is less, because that's the sort of the direction of how free energy goes and in spontaneous processes. Now the interesting thing is that there is another fellow, 𝗙𝗿𝚋, who is a professor of theoretical neurobiology in London, and he's sort of a pioneer in this, and he has said, okay, this Gibbs free energy, we can also formulate this in terms now of information processing. So now this is also a free energy. It's also an energy minus an entropy, just like the Gibbs free energy, but this now is a function of probability distributions over variables. And when we talk about probability distributions, we are in the realm of information processing, because probability distributions are functions over variables, and they describe which values these variables can take on and how, and let's say the information processing is how these probabilities distributions change as I make more observations about these data. So 𝗙𝗿𝚋 says this particular function here, this variational free energy now, he says, well, all biological spontaneous processes are governed by variational free energy minimization. And when he says all, he means all. So including perception and learning and selection or decision making and attention mechanisms, everything. Just minimization of one function. It's really a remarkable claim. I want to show two aspects now of this free energy functional. One is that if you take the concept of an energy and you multiply by a small instance of time or an interval of time, you get something in physics that is called action. And if you minimize action over time, that's basically you follow something that's called the least action principle. And the least action principle is a very fundamental way of describing physics. This is really at the bottom. You can derive classical mechanics and electrodynamics. You can derive most of physics, or you can describe most of physics as just following this least action principle. So that's very nice. Secondly, this variational free energy functional that 𝗙𝗿𝚋 introduces, if you minimize it, you recover something that's called Bayes' rule. And Bayes' rule is the rule for optimal information processing. This is the basic rule for how systems should learn from data or from other constraints. This is optimal information processing. So what 𝗙𝗿𝚋 then says is that, yeah, on the one hand, brains just follow the rules of physics. How could it be else? The interesting part is that under a few technical conditions, and they relate to Markov blankets, but brains submit to those conditions, so I push them aside. But under some conditions, then following this principle of least action actually leads to optimal information processing, to optimal machine learning or signal processing, what you want to call it. On my slide, I say it leads to automated, approximately optimal information processing. Well, the free energy functional in the brain is a function of millions of variables. And it's time varying because it's a function of the sensory data that hits your retina and eardrum. So you have a function of millions of variables, or even more than millions, and it's time varying. So you're not going to find that global maximum. You just try to kind of follow a trace towards the a minimum. But that's quite amazing. I mean, to me, this relationship between physics and information processing. Now, it's just a theory, but let's see how this actually impacts when we want to use this now to design a system, to design an algorithm. And let's say that I want to learn how to ride a bike. So we know that learning how to ride a bike happens just, well, you just start learning, you just get on the bike and you start riding. And through your eyes, you get sense, and also through your vestibular sensory organ, you get signals about the environment, and you interpret them. That's your perception. And based on your perception, you plan to make new actions, like turning your handlebars or moving with your point of gravity. And so over time, if you keep doing this, you learn how to ride a bike. So, and so 𝗀𝗍𝘀 says, and then what's happened in this perception and action compartments is just free energy minimization. Now, it's not about the math, but if I write down here now the free energy functional for perception, then this free energy functional decomposes, or you can decompose it into two terms. One term, which we can call Bayesian evidence, describes how well the brain has learned the problem. It describes how well is my problem represented, how well have I learned the data that's out there. So that's a cost function for how good your problem statement is. The other term is a 𝗙𝗿 divergence, but it's basically your cost for your solution. How well did I solve this problem? How well can I solve this problem by free energy minimization? So what the brain has, it has one cost function, and it has a cost for a problem, for your problem statement, and a cost for how well your solution, how well did you solve this problem? And that means you get away with a neutral cost function for basically solving all problems. Minimizing free energy means, on the one hand, you want to get a good problem statement, so you minimize the aspect of the free energy that leads to a good problem statement. And on the other hand, minimizing free energy also leads to Bayesian inference, and you solve your problem by doing inference in this model of your problem, and you also need to get to a very low free energy there. If you have a poor problem statement, high free energy for your problem representation, but you solve it perfectly, you didn't solve your problem. If you have a great problem statement, but you cannot solve it, then you still don't have a solution. You need to get a good problem statement, first learn the problem, and then solve it. And this free energy functional has that insight, right? So it's a really one solution approach to many problems. That's very different from engineering. In engineering, we're used to, when I have a problem, I go to the literature and I find 15 solutions, and I pick one, and then I change it. Now I have 16 solutions. The brain turns that around and says, I cannot afford to get a new solution approach for every problem. So rather, I have one solution approach, and then we'll see what the problem is. And if I don't know the problem, I will learn the problem because it's part of my cost function. But now we need to train the brain, right, to learn the problem. So I need to make actions. And the actions are also, the cost function for actions is also free energy. It's actually technically expected free energy for the future, because when we make actions, we are talking about, well, planning, right? We want to make an action to serve some future goal, namely learning the bike. But if I decompose that free energy functional for actions, I again get two terms. One term is basically the reward, the utility, namely make actions to stay upright, so to stay on the bike. That's the right action. There is another term in expected free energy that's an explorative term. It's a mutual information. Basically, it's information seeking. If I don't have a good problem representation, my actions are not aimed to stay on the bike. My actions are to get the data that will help me learn the problem, so that in the future I can make actions to stay on the bike. Again, the brain doesn't do this by tuning. Let's say there are no tuning parameters here. There is just free energy. The brain doesn't know that it needs to explore first and then explore. When you learn how to ride a bike, you just move your handlebars. You're not consciously busy with, I want to make an information-seeking action. I want to get data, or I want to actually serve my ultimate goal. It's basically transparent. There's only free energy minimization, but free energy minimization over actions includes both exploitation and exploration. In machine learning, this is quite a dilemma. They call it the exploitation-exploration dilemma, but it doesn't exist in nature. So we have here a cost function that has roots in nature. This is how nature works, or at least according to our theories. It leads to optimal information processing. Minimizing this cost function transparently leads to both learning the problem and then solving the problem. So you can basically have the same solution approach no matter what your problem is. And when we make actions to basically actively select data so that we don't have to collect a big database, but we just can learn from the optimally selected small data set. And these actions are selected both, let's say, with the end goal in mind and also explorative if we need to learn our model. So it's a beautiful cost function that has everything we really want in a cost function. So then this is our goal, at least the goal of our lab, rather than in the brain. Let's put it in an iPhone or a watch and let this iPhone now, I can put it maybe in a robot and let this robot learn how to ride a bike, or let this drone learn how to perform some smart task, right? I work for a hearing aid company. I will try to let this agent learn how to design a hearing aid, because a hearing aid is a very complex algorithm. We have lots of engineers in the loop, but an agent like this does optimal reasoning, makes optimal hearing aid proposals, will learn from the smallest possible data set. So it has all these good properties that we really want. So that's our goal. And basically, if we know how it works, then ultimately, yeah, we can use it anywhere, right? We can use it for self-driving cars or AR, VR. So that's our goal, to make synthetic, free energy principle-based AI agents that automate the design of signal processing systems and control systems in the field by self-organization, just by interactions in real time, no big database collection up front, just automatically, if you will. So now the next problem is, so how do we implement this? Because there's a bunch of formulas there. And if you go to the papers, you'll see even more formulas and lots of math. So how do we implement this? That's basically our research. So the thing to know about this is that the brain really is just a model of your sensory inputs. So we used to think that the brain would be sort of like a pattern recognizing machine. You get your inputs on your retina, and then you do feature extraction, and then you do classification or something. That's not how it works. The brain tries to predict sensory inputs, and then it reasons backwards from those sensory inputs to your, basically, what are the internal states that are needed to produce these sensory inputs, and these internal states that are needed in your model, well, that is your representation of the causes in the world that generated your sensory inputs. I can actually easily show that the brain has a model of of your sensory inputs. This is a famous painting. You see here a vegetable bowl, and if I turn it upside down, almost everybody will see a gardener first, a face, right? Why don't you first see here an upside down vegetable bowl? Well, because the brain has encountered in the world many more times straight up faces than upside down vegetable bowls. So we make much stronger predictions to see let's say, straight up faces than upside down vegetables. So your perception is this fusion of the data and your prediction. The data is compatible both with upside down vegetables and straight up faces. But our prediction is very favorable for, let's say, straight up vegetables and straight up faces. Right? So that's what we see, and that's because we have an internal model. What we see is not just dependent on, let's say, the sensory inputs. It is, for a large part, dependent on our own fantasy about what we predict we will see. So there's a model inside, and then we need to do free energy minimization in that model. And how do we do that? Well, that's another technical story, but what we do is we build these models, and then we write it down in a graph. You see on the right-hand side a graph, and then the math on the left-hand side is not important. It just shows that if you then do free energy minimization, you can associate the operations with messages, as if these nodes in the graph send a message to another node, and this node responds and sends a message to another node, and so forth. And that is the free energy minimization process. And that's, of course, very, I mean, at face value, reminiscent of, well, what happens in the brain. You have these neurons, and they're in a graph, and they send action potentials to each other. And so that's actually how we implement this. And so indeed, when we do this, and we've done this now for a simple task, namely design a dynamic range compressor for a hearing aid. And the dynamic range compressor is just a simple signal processing algorithm. As an engineer, you have 3 tasks. You want to design your algorithm. You want to tune all the parameters to fit this patient. And then you want to execute the algorithm, the fitted algorithm for this patient. That seems like 3 different tasks. Right? The parameter estimation is machine learning, and signal processing is something different. Not here. We just built a graph, and then we did message passing. And on the left-hand side, the messages lead to pruning of edges in the graph, which basically builds your algorithm, basically builds your graph. Then in the middle, you have messages that tune your parameters. That's your machine learning part. And on the right graph, it's basically the same graph, just at different scales. But the right graph, the signal or the message passing leads to signal processing. So there is just one mechanism, free energy minimization, and free energy minimization is always implemented just by message passing in a graph, and message passing takes care of everything, of building the algorithm, of tuning the parameters, and of the signal processing. This free energy functional is a function of the sensory data. We include feedback from the patient in sensory data. When a patient says, I like this, I don't like it. So our free energy functional is personalized. Everybody gets their own cost function, because free energy is a function of the data that I generate around me when I walk through my living room, and wherever I go, I get my own cost function, and everybody gets their own cost function. Yeah, so then we actually implemented this also for some other systems, right? On the left-hand side is Anouk, a master student who built a gesture recognition system. And in the middle is a master student, Barak, and he built an agent that basically learned how to park a robot at a particular parking spot. And on the right-hand side is an agent that is in a product. The company I work for, GN, is the mother company of Jabra that makes these headsets, and this agent takes your audiogram. The crucial thing is that in all 3 systems, and they're very different systems, underneath, there's just an agent, a probabilistic model that does free energy minimization, and that's all that's going on. And whether you talk about gesture recognition or building a dynamic range compressor or doing robot navigation, our toolbox, when it comes down to it, is just a graph that passes messages. Every algorithm at that level looks the same. Just like in the brain, whether you learn Japanese or ride a bike, it's just message passing, right? So, so that's what we've been working on, and we try now to scale this up to the future. So this is going to be my final slide. Currently, I'm taking here hearing aids as an example, but it's not about hearing aids. But we design many algorithms, signal processing systems in the world by engineers. Deep learning brings to the table that you can basically train them by data, but then you need to collect the right database, big database, and label it. But this, let's say, natural AI brings to the table is that we're going to design the designer. We're going to design an agent, and the agent will do the design. The agent is now in the real-time loop with the patient or with wherever this signal processing system is stationed. And there is a second loop with the engineer, but the engineer is not building the product algorithm now. The engineer just builds the designer, the agent. And yeah, there's a lot of advantages. Let's say the current method involves a lot of minds, right? We have tens of engineers in the loop, and the whole, I mean, if you count everybody else, you get close to hundreds. And this is completely automated. It's just a function that gets minimized in real time by message passing. As an engineer, you have engineers that specialize in feedback cancellation for hearing aids. You have engineers that specialize in noise reduction for hearing aids. So everybody gets their own specialty. This cost function learns to collect data to learn what the problem is and then solve it by inference, which is also free energy minimization. There's no need for big data collection. These systems actively seek for the data that they need to solve the problem. Because if they don't have a good problem representation, if they haven't learned the problem, if they don't have the right data, the actions that will be taken will be to find the data. It's like when I'm hungry, I can say, what's the solution? Well, I eat a sandwich. But if I don't know where my sandwich is, I need to first search for the sandwich and then eat the sandwich, right? So my action depends on if I know where the sandwich is, right? And so that's completely built in here. That's, I mean, there's no tuning parameters. This is just, let's say, completely transparent. And in the end, yeah, that leads to offline design cycles of that, in our case, can take a year, and that leads to unsatisfied customers and lots of costs. And in let's say the future, perhaps we get these agents that you can take everywhere. These agents have an informational advantage because where a situation goes wrong, well, the agent is there, but you can't send an engineer with every client to wherever they go, right? So, so I'm pretty hopeful about this technique. I think it's a very promising technique. There's a lot we can learn from nature. And yeah, I think within 4 or 5 years, we'll start to see these agents actually, hopefully appearing in industry. And then, yeah, we'll see how it scales. Thank you. Thank you.
Thank you very much, Professor 𝗱𝗿𝗀𝘀. Yeah, it's super intriguing topic, I have to say. I think, yeah, from the projects, the AI projects we have running, I see a pressure to reduce the need for big data, and indeed, for example, through interaction with a domain expert, active learning, try to achieve this. But the self-learning aspects of this new AI basically is very intriguing to me. Thank you very much for a nice presentation. As I've mentioned up front, we are also very curious to hear your questions and discussion, but we will leave that for at the end of today's meeting. I would first like to ask Bas van der Linden to come to the stage. So Bas is our technology director at Sioux, and he has a long-standing track record in the architecting of systems and software with an advanced modeling and optimization component in it. And today, Bas is also managing our technology roadmap at Sioux, where AI plays an instrumental role. So I'm really curious to hear how today's AI looks like and what we have to do to incorporate the promise of such advanced new techniques. Bas.
Okay, thank you, Robert, and thank you, Professor de Vries, for the enlightening talk. Looking forward to the questions section, because I had a lot of questions popping up myself as well. Hi, I'm Bas van der Linden. I'm CTO of Sioux, and I'm forming the bridge between technology and business development. And that's, in that shape, I see a lot of AI projects coming by throughout all our departments. And from that, I learned a lot. The three things I want to tell today are hardware will join software in the way it's being developed. And I'll explain what that means later. As you've seen with Bert, machines are becoming beings, and that involves that we have to analyze systems differently. And maybe the main message is what we've seen the last couple of years of what happened with AI. It's really just the beginning. There's a lot of things, different things happening, different techniques popping up. At Sioux, we have 5 technology programs that we designed to cover all the areas that we're active in. And none of them is called AI, actually. So there's no, we have sensing and detection, digital twinning, data technologies, extreme positioning, digitized engineering, but there's no AI. And this is because AI is essential to each one of them. Now, sensing and detection, I think everybody's aware of where AI is good at the current state, and so classification of images, that makes sense. I think also digital twinning and data technologies, they don't need a real explanation how you involve AI there. And I think in this talk I will show a bit why I think exactly extreme positioning, so very precise positioning or positioning in complicated environments, high vacuum or very precise, we will need this new AI techniques. And finally, also the digitized engineering. So if we automate our engineering process, how does AI play a role there? Now, first let's look at why AI, why is it being talked so much about? There's been a large success, and people think usually it's because the rise of computing power and the design of certain algorithms. But if you look back, the algorithms, they started in the 40s, and we didn't change that much of them. Well, we made some clear improvements. Computing power has become more powerful, but if you look back, AI, it could have taken off in the 80s if the people who were trying to do deep learning back then waited a bit longer, and but it didn't. Something else happened. In the 70s and 80s, large databases, salary systems were automated. So by the time that AI started to pop up, we were used of having large data sets. There's a second thing. When social networks came about, we started to get large annotated data sets, because people said, oh, this is my cat, this is my dog, and now all of a sudden we had large annotated data sets. So this availability of data has been the main driver of the advent of AI. But there's something else happening here, and this is not very visible, and in a way it's on the algorithm level, and I think AI is the first step of our first steps in applying mathematics in a nonlinear way. So hidden inside neural nets are activation layers, and they are nonlinear. And what we always have done, we're using matrix operations, we always could find optimal bases and stuff like that. And now we start to do that in a nonlinear way. And this is, I think AI is just the first step of exploring that. And there's a lot of things we don't know yet about how to deal with that. A final thing, and that was also in Professor de Vries's talk, is dealing with uncertainty. And this is on different levels. If you look where AI became successful, it's especially successful in this, proposing a nice advertisement for you for what you want to buy next. And it's not so critical if it's only 80% accurate. So in the use case where we used it first, AI, it was accepted that it was not very good. But now that we start to use it in an industrial setting, we want it to be 99.999% accurate. And we have to know a bit more. Uncertainty in mathematics, we know, we arrive at physics that we know are not knowable. In quantum mechanics, essentially probabilistic, at the bottom of all things, there's a probabilistic distribution. We cannot know everything. A bit more practical on a bit higher level. When I had my education, material parameters were still called constants. But if you do that and you have to position something on a nanometer, it's no longer the case. So we have to know how uncertain we are on these topics. Now, AI, of course, has a lot of success stories. So I'll quickly go through some. In image classification, we see that's a lot of success. So here we see two examples. One is for, we look at a signal from an ECG, and we can even see the heartbeat of the fetus, even if there's a lot of noise, for example, from contractions of the mother. And another thing, digital pathology, digital assisted pathology. There's no AI yet that can sit on the chair of the pathologist, but we can help the pathologist become faster. Their AI is becoming very successful. We can detect suspicious areas very quickly, and we can help pathologists to become more accurate themselves. Another field where AI has taken off is the prediction of if we have a measurement system to detect anomalies. And anomaly detection is the first step in real predictive maintenance. I want to predict when something fails. Now, we know that's essentially a very complicated problem because all failure mechanisms are exponential in nature, so you really only see it at the end. And there's some tricks you can do to go ahead. But quite often, you see problems coming by seeing, hey, the system is not responding correctly. This is very difficult to do with heuristics because there's a lot of different cases, and typically an anomaly is something that you didn't expect. So if you use people to find, let it find, they would have designed it differently. Finally, something where AI has become very powerful is to use as a model. So often we think of models we build from physics or from mathematics, we build it up. But sometimes things are just too complex, and then we can use AI to build a model. Just to represent the data, we have a large set of data, that Bert already gave it. We apply that in a couple of different things now. There's one for a company called Snapit. We looked into making a model of a student. We used to have heuristic models, and these heuristic models were based on psychology of what we know are kids. But these models are don't have the quality of physics, right? It's not a drop an apple and it will fall. When we moved there to a deep learning model, so just capturing the data, reproducing the data, also tuning the model to individual students, we got a big success. Same thing we applied in Amsterdam, and now for the case of garbage containers. It's a bit different from students, but can use the same mathematics. And garbage containers, we wanted to fit them out with a sensor to know how full they are. But these sensors are very expensive, they break, you have to replace them. So we thought, like, can we put a virtual sensor? Now, we use a lot of input data. We have a couple of real sensors as well, so we can fit the model. And now all the containers have a sensor. It's virtual and it's not real, but it takes a lot more input. And it's not looking only at how filled is the container, but it also knows, hey, it's a holiday next week, or typically on a sunny afternoon, there's more garbage being thrown away. this is also an example where AI is successful. There's a couple of difficult things, though. If you, what I said here, you have a lot. You need a lot of data, and it starts with collecting data. And we see there's a lot of companies making a lot of effort to get the data out. But having the data is not enough. You need to look for the value. What is the value inside the data? And sometimes it's better to know that a priori. So you collect only the data that's useful. Not always, so some people think it's good to have, but it's making especially hard disk providers very happy. You have to design the process to add this value, and you have to have a factory to add its value. Now, this has been partially solved already in practice. IoT is a big thing, and we have dashboards, and we can look at a lot of information. And over the past years in the software world, something came up that's called DevOps. One of the main parts is continuous integration, continuous deployment. So we continuously improve software. And a lot of data is being collected. That's IoT, is basically you collect data, and the people from industry will ask the developer, hey, can you add this to your dashboard? So then we can look at that. And they will add that to the business intelligence part. What you need to unlock the true power of AI is to have make it into MLOps, machine learning operations. There's a second thing that if the data comes in, you need to have it in a second loop where data scientists and data engineers process the data into new models. And this is something that we do now with big data. There's another problem, though, with AI, and this is not talked a lot about, or not even realized a lot, because we do all this, most of the successful AI things we do in the cloud, and then it's far away and we don't see. But there's an enormous energy usage associated with AI. Typically, if we want to do an AI project, we always choose the latest, greatest hardware, and typically that means also a lot of watts that we burn. Yeah. From the other hand, and this is the universal approximation theorem, and then I have to correct Professor de Vries, that with deep learning, so the FX here on the bottom means it's a deep learning network, and the thing on top says it can do everything. So if you wait a lot, it can do everything. What it doesn't say that, what it also says, it can do everything if n goes to infinity. And this is the catch. And infinity is very expensive. And we kind of see that now deep learning is great, but it's almost always more expensive than if you have a hand-designed algorithm. And this is something that we need to address. Yeah, this is what we called edge AI. There's another problem. So this energy consumption, you don't see that in the cloud. That's difficult to see. What we often more see is that we do, when we do a project, for example, in self-driving cars, you just take a big computer, fat GPU, and everything is good. But when your product is finished, now comes the next step. Okay, you cannot ask everybody to drive around with a big computer like that. So you have to take people through the process of how to go to smaller, more affordable hardware. So the main question is, you did a successful pilot, and now the question, only then the question starts like, how do we bring it further? Okay, now at Sioux, this is our current bread and butter. Typically, you have to choose between CPU, GPU, FPGA, or one of the new and upcoming chips. Now, the things on the left, the CPU, GPU, FPGA, are quite general purpose, and we see an advent of ASICs coming up, which are much more cheap. So a GPU, FPGA is in the order of €100, 1,000 euro. TPU is now 10 euro. If you design your hardware now, typically for automotive, you would like to use a TPU now. The next year, I think I would go for something from the Grey Matter Labs here in Eindhoven, the sparse inference. That's promising. That's in 2 years I would like to use that. In 4 years, I would like to do something else. And this introduces a problem in hardware design that we are facing now. Hardware will have to follow software development because the things that we can use today aren't available in 2 years. It's not just that the old strategy is something to fix a design, keep it for 20 years the same, make sure that your supply of goods is good enough, but this is no longer viable. So with processors, you can still get 10 to 15 years that are available. With all this new hardware, GPUs, FPGAs, they don't have a long lifespan. So they burn, basically, after a couple of years. And you will have to replace them after a couple of years. But there's no incentive. There's lack of space in the fabs. There's no incentive for the makers to keep producing those things. So we have to design hardware that takes this obsolescence and not just that component, that specific version number. No, now I use a TPU, and in a couple of years I have to use a completely different type of processing unit. This is something at Sioux. We're looking into that. Our ClickBricks architecture is trying to tackle that. So it's you have to make a bus, so you have to see where do I do my AI processing, and that AI processing has become modularized. So I know I can replace it. I don't have to replace a whole machine, but the AI, well, always want to use the latest, greatest, because to get the performance, I have to design in my machine that I can replace it for the next year. In the 50s, Boulding already made a distinction between complexity of system levels. So he started with a framework. Framework is basically like the chair that at least the audience here in the live environment is sitting on. That's called a framework. It's like static. It can be complicated to compute how it works, but it's still a pretty simple object. Then you go to dynamic system. Then you go to a feedback system or a cybernetic system. And here in the Eindhoven region, we have been used in these feedback systems. They're complex, and we have made system engineering approaches that deal with how can we solve these feedback systems. Now, already in the past decade, I think, so for example, at ASML, the complexity became bigger than that. There's no one at ASML that there's no architect anymore that oversees the whole architecture. So it has become an open system. So every subsystem has an environment around it that it can't fully predict. So this uncertainty enters into your system design. Now, if each of these subsystems, if we supply that with AI, they become sensing and directing things, which in Boulding he considered animals and human beings, sensing and directing. But they start to get a goal they want to optimize. Yeah. So, equipping machines with an AI and making machines cognitive, that they have a goal, that they want to optimize something, means that we have to look at the system design on a higher level. These things are becoming beings. They will move to a certain place to find their optimum. So if you then combine things, now we don't have a lot of tools to deal with societies, so to predict how societies work, except for AI. So AI will play a big role in getting these machines under control. Okay. Understanding machines is understanding people, and this is what we do. If you make agents cognitive, it starts by trying to predict what people do. One of the nice things we work at now at Sioux is to make recipe development faster. So we want to take the lab work, people take decisions. We can add this mathematical layer underneath, and we're speeding up. So instead of doing experiments and in the food and the chemical industry that can take up to 2 to 5 years to change a simple recipe, we can speed it up to 2 months. Another exciting thing that we're working on is external human-machine interaction. So now if an AGV is driving around, typically you put a flashlight on it, which says I'm dangerous, and the only thing that you can do as a person is to stop. You can only stop and then become less productive. And this is not good, of course, right? Because we want people to be productive. So external human-machine interaction, you want the machine to talk to the people around it, like, hey, I see you, please go ahead, or don't go ahead, because I will continue. And this is the kind of interaction we have with our fellow drivers. We're building this now into, and it takes understanding what the machine sees and projecting that. Also understanding what people do. Are they crossing the street? This one I had to take out the picture of babies. So we're looking at epilepsy detection in infants. And this is, for me, I find this a very relevant project. There's not a large market behind it, but still this is something. It is, epilepsy is a very complicated disease, which is not, you cannot detect it on the moment, but you have to see in a large stretch of time in which state do we come. And also there, you start to track people and you see which state they are and predict them. Okay. My final slide is, these are all still examples of AI, but there's other upcoming related to AI technologies that we need to do. The talk of Professor de Vries still talked about people and learning how to do if in the context of dealing with people, but we also have to focus if we go to a very low physics. For example, if we work with plastics, plastics always different. Like every time I get a new batch of plastics, they behave slightly different. So even if I design a machine completely that works the way it's supposed to work, I don't know the exact consistency of materials. So I have to learn that. And there's a couple of techniques that help us there. Like I want to mention Koopman operator theory, because that's very relevant of making these large complex simulations compact enough to use them inside the loop. So I'll conclude my talk. AI has a base in data. At the bottom are nonlinear math, and I hope that last slide is another version of nonlinear mathematics that's coming up. Uncertainty or probability is becoming essential to take that into account. So I would like to conclude here, Robert. Yeah.
Thank you very much, Bas.
Yeah.
I hope your talk has also inspired the audience. We've seen quite diverse examples passing by, AI to interpret images in biology, pathology, but also anomaly detection in fleet monitoring, or even interaction with human beings in the example of a car that can detect a crossing passenger. So, pedestrians. So, thank you very much.
Thank you.
At that time, I would like to ask Professor Bert de Vries, Ruben, Stijn, if you could also come forward, because I would now like to see if there are questions from the audience. And I've already seen that in the chat online, we have several questions being posted. But maybe it would be good if someone from the audience could kick it off. We have a microphone there in the middle, so if you have a question, please feel free to grab the mic and ask our speakers a question.
Hi, I'm Robert. I have a question for Professor de Vries. You talked about the energy minimization equations, and also talked about a graph, and I was wondering, what do the nodes in that graph mean, and how can I build one? Or should I build one?
Yeah, the graph, in this case, is called a vector graph. And that means that so each node is a function of variables, and each edge is associated with the variable. So let's say I have a function of 3 variables, a node. That means that this node is connected to 3 edges, x, y, z, and maybe there's another function, g, that may also be a function of x. Well, then that's also connected to x. And then the total graph is just a multiplication of all these functions to make a big multidimensional function. Now, if that is a probability, if these functions happen to be probability distributions, then you've built a big probabilistic model, what we call a generative model, for let's say for the sensory data. And the idea of a generative model, so a probability distribution over all your variables, is that you can basically almost every task that you want to do, you can phrase it as an inference task. Let's say classification or regression or whatever the task is, making actions, you can phrase it as an operation on this big model, and that operation, well, can be phrased as inference, and inference can be executed by free energy minimization, and we do that by message passing. So that's, it's complex, but there is the graph is the model, basically, and free energy is executed by passing messages over the edges. Yeah? Okay.
Okay.
I have also a question for Professor De Vries. My name is Hans. With, let's say, traditional AI, you also have the chicken-egg problem. So you need data to make optimization, to learn from it, to improve a process. But in the work we're doing, we started with new products, new machines, everything is new, with a blank sheet of paper, literally. So in the approach that you envisioned, can it just switch the thing on and it starts learning and making progress? Or what's the starting point in your approach?
Yeah, the starting point is this generative model that contains all the assumptions you have about how the data is generated. That could be just a neural net. But if it is a big neural net with n is large layers and you have wide layers, then you make very few assumptions, very few structural assumptions, and you have to learn a lot of parameters. So what the graph allows you to do is to start with a sparse graph and say, well, I know that this variable is not related to this variable, so you can start with the sparse graph and then do your learning from there.
This is made by an engineer, or this is automatically generated, this graph, or the sparsity in the graph?
Currently, it is the engineer that generates the graph, right? Now, in nature, you could say evolution is also free energy minimization over a longer time scale. So we have structural adaptations in the brain, right? That would be the structural adaptations in the graph, but that's technically difficult at the moment for us. And then we have, of course, procreation, building completely new graphs through combining other graphs. So that's also, let's say, evolution and natural selection is also free energy minimization. So in nature, building these graphs is automated. In engineering, at the moment, you have to build your graph and set your assumptions in your model. And then, or you can do a little bit of structural adaptation, but it's still difficult to just, let's say, start from scratch and just let it go.
So the role of engineer still not finished. That's happy.
Yeah. No, not at all, not at all. I hope that in the future, let's say, engineers get more of a role of designing the designer, designing the agent, and the agent designs the production algorithm. But there will still be lots of engineers in the loop, just at a higher abstraction level. Yeah.
Okay, thank you.
Maybe, hi, I'm Mark, by the way. Maybe a short follow-up question on this one. Could you sketch how a solution based on your technology would look like for the drone show actually that was carried out at King's Day? I mean, just to sketch a little bit how a system would look like that uses your technology to make that work, and how long do we need to wait to actually...
Well, you can try to carry it out. So then, yeah, I don't know enough about the drone problem to map it one-to-one, but I can imagine that, look, a drone can contain an agent. The agent can have sensory inputs. The agent can just look at the gestures, has a gesture recognizing, or learns how to recognize these gestures. For instance, you would have a drone. The drone doesn't know anything, and it can see by radar or by a camera, the gestures, and then it just starts moving, or it infers how to move. And if it gets, say, if the lady who does the gesturing can say no, 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 then this drone will actually eventually learn to make the correct actions based on her gestures, right? And the interesting thing is, like humans are connected and we exchange information through language, you can also connect these drones. So if one drone has learned how to interpret gestures, then you can connect the drones and get a bigger agent, a multi-agent system, and they can learn from each other, right? And they don't have to learn everybody, or not all the drones have to learn all the same thing, but they can stay and learn from each other. So that's sort of how you build these, I think these collaborating drones, right?
Okay, thanks.
Sure.
Maybe that's a good link to the drones. I see in the chat also some questions being posed. Guys, I think best to you, by Giovanni Mariotta. Technical question about architecture and design. Is your solution scalable with more drones? Is it a distributed logic or centralized by one server that drives all the drones?
Yeah, it is indeed not very scalable. So it is a centralized system. So we have one computer which calculates what every drone has to do. But this choice was made because also, so the way we determine the positioning, this motion capture system is also made for small-scale environments. So we decided to do it centralized because that's faster and easier, and then you can also better keep in account what every drone is doing. And we couldn't scale it up anyway to above 25 or so drones, because then there would be too many drones physically close to each other, so they wouldn't be able to move without colliding.
Okay. Maybe another question being posed here. How do you test the solution? If an error happens like we saw there, do you every time need to replay the sequence with the actual dancers?
Yeah, that's essentially what we did. During the testing, we did multiple tests on different areas of the show. We've got the pre-programmed path, but also the live interaction. But for the live interaction, we had to test it ourselves, put on the motion capture suit, and then try a couple of things. Many things went wrong. We added the solution and then tried it again to see if it worked. And in that way, we managed to solve a lot of the issues.
And I also think what was really instrumental here is that we just basically logged everything which we were doing. So we could basically get back, we could see what was happening and hopefully figure out somehow what went wrong and basically try to fix that and then try again.
In the chat, I see some questions to Professor de Vries still. A lot of questions by Dave Berendhuizen. Let me see. Let me, in view of time, pick one, I guess. How do you define the reward system for the optimization of the design by natural AI?
How do you design the reward system? So let's say in the case of the hearing aid, and I sort of in reinforcement learning, you actually make a big difference between, let's say, sensory observations and then rewards on the side, right? Yep. That's not how natural AI works. Rewards are just sensory observations. And so the brain is a model for sensory observations, and the brain wants to predict sensory observations, but there is a twist. We actually have a preference for future sensory observations. I want my body temperature to remain about 36, 37 degrees. So I'm going to predict that I'm going to be 37 degrees in the future, and then I will naturally infer actions to make that come true. So if in the hearing aid case, if I predict that the user is going to give positive rewards in the future, then I can infer with my model, that's what free energy minimization does, I will make actions to make that come true. So that's how I reward her, just by having it encoded that she's going to be happy, or that I'm going to stay alive, or that, right?
So this is actually a big difference between reinforcement learning and self-learning philosophy as you've presented to us.
Yeah, there is no explicit reward function. There is only a model, and you can encode in the model, you can encode preferences or priors in Bayesian probability theory. And with these priors, you can also prove that anything that you can do with reward functions, you can also do with prior probability distribution.
Very intriguing, I have to say. Maybe given time, a final question. What's the order of magnitude of the number of the nodes that you use in, for example, the hearing aid application? How does it compare to the neurons in the brain? So I guess this has to do with the scalability of this kind of techniques at the moment.
Yeah, the number of neurons in the brain, I think, is in the order of 10 to the power of 14. So we're not even getting close to that. No. Our systems have hundreds, maybe thousands of nodes. We're building a toolbox. So this it goes like hand in hand, right? The scale of the applications that we can do depends on how good our toolbox is in minimizing functions of thousands of variables. We're building a toolbox now that works, let's say, the nodes are they're reactive and they're sort of, they just react. So that means they don't do anything unless they get hit. And that's much more scalable. So we hope in the future to be able to run systems with tens of thousands, maybe 100,000 nodes, but not at the moment.
Yeah, the examples that your students have generated are like what?
Yeah, they are concepts, right? The gesture recognition, I think we trained it to do 18 gestures, and the robot, of course, is just on a table. There is an industrial application for Jabra, for the headset, but it's a small application. So they're small applications. And it's not like, let's say, driving a car yet.
Yeah.
Right? But
some challenges left for us as industrial partners to implement these tools and scale it up. One final question for the audience. I think it's 6 o'clock slowly. I think it's time for me to thank our keynote speaker of today. I have a small gift for you. Thank you very much for presenting today. It was very interesting. Bas, Ruben, Stijn, I would also like you for your interesting presentation. You as an audience for your attention, at home as well. We hope to see you back next at one of our next Hot or Nots. In case of further questions, discussions, please feel free to contact us. We'd love to hear you. And for the audience here, let's have a chat afterwards. Thank you very much, everybody. See you next time.
stopped